law of refraction on the basis of wave theory. Let us see how Huygens explained laws of refraction based on his theory, wave theory of light. So, let us see, we start by considering an interface x y that separate two medium of refractive index n1 and n2. A plane wavefront AB is incident on the interface x y at certain angle theta. Let us say this is the normal. To give you the sense of the direction of the wavefront, we introduce the ray, the concept of ray. So, this is the ray. Now, this wavefront is A and B. Let us bring in another wavefront, another ray, which is passing through the center. The wavefront is incident at the interface at an angle I. That means this angle is I. So, according to Huygens, every point on the wavefront acts as a source of new disturbance, which he named it as secondary wavelet. So, when the wavefront strike the interface at A, ripple is first produced at A. Okay. So, this ripple travels in the medium 2 with a velocity v2 and covers a distance. You should not draw that. Yeah. So, it travels inside the medium 2 and pass very close to the normal, such that it subtends an angle r with the normal. So, this is the angle of refraction. Now, in terms of wave theory, the ripple produced at A travels or grows or describe a hemisphere of radius, how much of radius v2t. That means it gradually grows like this. So, this radius will be v2t because that is the distance. Okay. So, we can, with v2t as the radius, that is the distance covered, we can draw the wavefront like this, the refracted wavefront like this, because this is the radius v2t. Okay. Now, by the time the wavefront, the secondary wavelets from B reaches B prime, the wavefront from A has already reached up to this point A prime, which is described. That means the secondary wavelet has described a bigger hemisphere of semi hemisphere of radius v2t, v2 being the velocity of the secondary wavelets in the denser medium. Same thing for the intermediate wavelets coming from some other points from the wavefront. Okay. Now, so you can see that v2 and v1 is the velocity of the light wave in the medium 1 and v2 is the velocity of light wave in medium 2. So, if n1 n2 is greater than n1, that means v1 is greater than v2, that means velocity of light in medium 1 is greater than velocity of light in medium 2. So, as a result, the wave fronts, the secondary wavelets in the secondary medium, in the denser medium N2 will travel at a lower velocity compared to its velocity in the medium 1. As a result, you can see the ray is bending or moving close to the normal and not like in case of reflections. Okay, so it is going close to the normal. So the circles or hemispheres described inside the denser medium will be little bit shorter compared to the one which will be described in the medium 1. We will elaborate this through animation. So right now you can concentrate that. So if this is R, so we can see that when this plane wave front AB strike the interface, as the point A strike the interface first, so it generates ripples or it generate hemispherical ripples of radius how much v2t, which travels in the denser medium with the velocity v2, and by the time the point B on the wave front AB strikes at A prime, the ripples originated from A will grow to a greater dimension, will grow to a greater radius, and will, if we draw now a tangent, we will get the refracted wave front A prime B prime. Understand? So, but does it hold the Snell's law? Because for the law of refraction to hold, it must obey the Snell's law. In order to prove the Snell's law, let us complete the diagram. So this is the normal in this side. So the ray, so we need to draw. So now, so if this is R, this angle will also be R. If this one is we have seen earlier that this one will also be I, and this is R means this is R. But how? To explain this, you can complete the diagram like this. So this is the direction of the refracted ray inside the denser medium for this side, for the right side. So this angle again will be R. So this is R, this must be 90 degree minus R, and this is 90 degree minus R, this must be R. So now using Snell's law. So now if we use Snell's law, we can write sin I by sin R equal to, so the ray is going from rarer to denser, that means N2 by N1, okay, equal to, so this is Snell's law, right. So now what is sin I here? This is Snell's law. So what is sin I from a? Sin I would be perpendicular by hypotenuse. So let me do it here. Sin I will be perpendicular by hypotenuse. Here perpendicular will be A B prime, B B prime by A B prime. But what is B B prime? B B prime is V1t. So we can write this as V1t by A B prime. Sin R will be how much? Sin of R would be again perpendicular by hypotenuse. So this being the perpendicular, that is A prime A prime by A B prime. So this one would be V2t by A B prime. So if we take the ratio, what do we get? So it will get V1 by V. So if we take the ratio, sin I by sin R gives me, you can see A B prime get cancelled, B B prime by A prime is there, that means V1 it is V1 by V2, which is, So it is n1 2, right, n1 by n2, which is, we can take the reciprocal and write this is 1 by, actually 1 by n2 1, right, sin I by sin r. So you can see this, we are going into the next medium. So V2, let me just see, I think I have done some mistake here. Sin I will be perpendicular by hypotenuse. So perpendicular is V1t by hypotenuse is AB prime, AA prime, okay, AB prime, and sin r is this. So sin I by sin r, B prime, sin I B prime. Yeah, we have done right only, no problem in that. So V1t by V2t by AB prime, V1 get cancelled, so V1 by V2. So V1 by V2, so V1 by V2 will be, V1 is N1. Oh, okay, sorry, I am done right only. Sorry, I have done, it is the absolute refractive index only, sorry. It is absolute refractive index only, I have done right only. So this is relative refractive index only, right? Because relative refractive index is defined as, N21 is defined as V1 by V2, velocity of the medium in the rarer medium to the velocity of medium in the denser medium. So it is correct only, sorry, I just was thinking something else, I just was running to keep the video short. So this is N21, which is nothing but N2 by N1. Hence, Snell's law is proved, right? So let us see this in animation. Let us see this, how this exactly it is working. Let's see this. To see, observe it. You see, this is, to know more about it, to know the actual detail, you can always refer the chapter 3 of the treatise of light, okay, by Huygens, Becquerel Huygens. Now let us come to the animation. Here you see, we have that same animation as we have seen in case of laws of reflection. Here you see, let me bring it back to 0. So let me play. This is the incident wave front, which strikes the interface, and as it strikes, it generates small ripples. As definitely the one which is first will grow over time than the one corresponding to the next one, which has been disturbed little later. So as you can see, this one is the refracted wave front. This is the refracted wave front, and this is the incident wave front, and consequently this is how it is getting refracted inside the denser medium. If we can change the refraction, refractive index, see what happens. You can see the ripples will be, the radius of the ripples are more. Why? Because V2, this distance is V2t. So that means V2 is the velocity of the light in the denser medium. So if the we know refractive index, if refractive index is more, velocity will be less, and if refractive index is less, velocity will be more. So if it is 1.8, so the ripples radius is also more, and so on. So and if the refractive index is more, ripples will be less. Clear? So this has been exhibited by this slider over here. You can see as the refractive index is increased, the ripples radius is also decreased. Understand? So this is, now let us see both of them together, reflection as well as refraction. You see, both reflection and refraction according to Huygens wave theory of light. You see, the ripples on the rarer medium is the diameter, the radius of the ripples or the hemispherical or the hemisphere is quite large in the rarer medium than in case of the denser medium. So these ripples diameters are more compared to the diameters on the denser medium. It is because the velocity of light in the denser medium is less compared to the velocity of light in the rarer medium. So, this is how Christian Huygens imagined that how the reflection, the propagation of light through a medium takes place. Okay. Let us go back to the board now, and this is how we prove the Snell's law. So, how do we prove it? We consider that there is a plane wavefront AB which strikes the interface xy and it gets refracted inside along A prime. Okay. Every point on the reflected wave of the incident wavefront acts as a source of new wavelets. These wavelets on striking the interface give rise to small ripples. By the time the wavefront, the secondary wavelet originating from A reaches A prime with a velocity v2t, with a velocity v2, the wavefront from B reaches B prime with a velocity v1 and describe a ripple of radius v1t in the rarer medium. Whereas, in case of the wavelet originating from A, it describes a ripple of radius v2t inside the denser medium. Now, if we draw a tangent over this ripples or circle, we get the refracted wavefront inside the denser medium. Now, clearly we can see, we can say sin I by sin r, we can take the ratio and we can see the Snell's law is obeyed. As Snell's law is obeyed, we can say the law of refraction holds, and definitely the first law of one of the postulates of the law of refraction is that the refracted ray, the reflected ray, the refracted ray, the normal and the incident ray all lies on a plane. Definitely all three, the plane wave front, the refracted plane wave front and the normal all lie on the same plane. Hence, the law of refraction is proved based according to Huygens wave theory of light. I hope I have been able to explain it to you. If you have any doubt, please reach to me, raise your doubts. You can raise it on the comments, or you can contact me and ask your doubts. I will definitely clear it. Okay. If you like this video, please don't forget to like it. Thank you.